Alright, so in this video we're going to talk about temperature, density, and conversions and how we can mathematically convert between one unit and another. So first, the definition of temperature: it is a measurement of molecular motion. Okay, also can be defined as the average kinetic energy. Okay, so it's the motion of molecules. So if something is hot, that means the molecules are moving very, very fast. And if something is very, very cold, the molecules are moving very, very slow. Okay, the difference between temperature and heat is that heat is the transfer of thermal energy between two objects. Okay, heat always flows from the hotter to the cooler. Okay, and so we can measure the actual temperature of an object when there is heat being flowed between two objects. Okay, so you can measure the temperature of an object, but heat is actually being transferred between two objects, and its temperature may be changing as well. Okay, there are three different temperature scales, and we commonly may need to convert between the different temperature units that are given in any given problem or scenario. Okay, the first one is Fahrenheit. That is degrees F notation there. That's the most common used in the US, and we commonly use that in weather that you may be familiar with. The next one is Celsius, okay, and we commonly, scientists commonly use that, and many other countries use that as well, other than the US, okay, so a lot of the values that we obtain in the lab on a thermometer, we usually record in degrees Celsius. Okay, and then the third is Kelvin. This is also known as absolute scale, and this is denoted by a capital K. Okay, 0K is called absolute zero, and that is the coldest possible temperature. The Kelvin scale avoids negative temperatures, where the Fahrenheit and Celsius we can have negative temperatures. Okay, so the three different temperature scales, we can kind of see pictorially right here the difference between the three. So you may be the most familiar with Fahrenheit, and so you might think in terms of weather. We know that rain will begin to freeze into snow at 32 degrees. So this is the freezing point for Fahrenheit, and the boiling point would be at 212. That correlates over to the Celsius. 0 degrees is freezing point, and 100 degrees is the boiling point. This is for water. And for Kelvin, you can see that it's a difference of 273 Kelvin difference. And here we would add on 273 to 100, and that would be for the boiling point 373 there for Kelvin scale. Okay, so there are a couple different equations that we can use to convert between temperatures. These two here are conversion between Celsius and Fahrenheit. Okay, so if you know the Fahrenheit temperature, you would plug it in here, and that would output the Celsius. If you know the Celsius temperature here, you would put it in this equation. It will give you Fahrenheit, and both of these are interchangeable. You just do some algebra and rearrange for the other variable. Okay, so for Kelvin, the link for Kelvin is through Celsius. Okay, that is the typical equation that we use. And so you take the Celsius temperature and you add 273.15 is the exact number, and so really this over here should be 0.15 there. Okay, so 273.15 to the Celsius gives you a Kelvin temperature that corresponds to that, or you could have the Kelvin temperature and subtract that number to give you the degrees Celsius. So you might ask the question, how can you convert between Kelvin and Fahrenheit? Right, so here we have Kelvin and Celsius, but we are given a Kelvin and we want to know what its Fahrenheit temperature is. So you have to go through degree C, right? Because we know that degree C correlates to Fahrenheit, and that equation up above there, you can use one of those. So you know the Kelvin temperature, so we would start with this equation here. We're going to subtract 273.15 to get our degree C. And then I'm going to use the Fahrenheit here because I want that equation. And I'm just going to plug that in, the Celsius temperature in here, and then just plug those numbers into my calculator to get my Fahrenheit. Okay, so before we get into what density is, we have to talk about volume first. Okay, so the common unit for volume is usually liter or milliliter. So liter is a capital L, milliliter is lowercase m, capital L. Volume is just the measure of the amount of space that's occupied by some object. Okay, and the relationship between liter and milliliter is the liter is the larger unit, the milliliter is the smaller unit. So I need 1,000 milliliters to equal a liter. Okay, so that is a conversion right there that you would also want to memorize. Okay, all right, so let's consider a large cube here. So the large cube outlined in black, I have a 10 centimeter height, 10 centimeter width, and 10 centimeter length cube, okay? And if I wanted to calculate the volume of the large cube, I would use the way that we calculate volume, length times width times height, right? So I could calculate that by, 10 centimeter, 10 centimeter, 10 centimeter, and I would get 1,000 cubic centimeters. Okay, so we can have units for volume other than liters and milliliters if it's in terms of a distance of something. And that means, the measured distance of the length of the object, okay? And so that means that that is how much volume can fit inside of that cube, okay? Now, if I had small cubes, like this one highlighted in red right here, and this small cube was a 1 centimeter by 1 centimeter by 1 centimeter, okay, in terms of its volume, how many of these small 1 centimeter cubes could I fill inside of the larger cube? Well, right here we've just calculated. We could fit 1,000 1 centimeter cubes inside of this large cube, okay? And so when you see that cubic unit there, you just want to recognize that that is a unit of volume, and volume is not exclusive to liters and milliliters. And this calculation here allows us to then develop the conversion factor between cubic centimeters and milliliters and liters. And so it turns out that 1 liter that's equal to 1,000 milliliters is also equal to 1,000 cubic centimeters, and we can reduce that down as 1 milliliter is also equal to 1 cubic centimeter. And so this is a conversion factor that you definitely want to memorize, and we will use that very often and frequently. Okay, so now that we've talked about volume, we can learn about density. Okay, so let's ask a little riddle question here. Which weighs more, a ton of bricks or a ton of feathers? What do you think? Right? Neither. They both weigh a ton, right? A ton, right? So if you answered bricks, then you may have confused weight with density, okay? Density is calculated or measured the mass of a substance divided by the volume that that mass displaces. Okay, so it's mass divided by volume, or we can abbreviate here, density mass over volume there. Okay, and the units, we would have a mass unit such as grams on the top divided by the volume, usually milliliters, so grams per mil, or commonly grams per cubic centimeter. Either one is commonly used interchangeably. Okay, all right, so this little calculation right here to get density, we also can use density as a conversion factor to convert between the mass of something and the volume of something, or the volume of something to get its mass from that. Okay, and density is also known as an intensive property. This is just a little side note. An intensive property is a property that does not change depending on the amount of the substance. Okay, so we can use density as a way to identify an unknown sample. Okay, if we can determine the density of an unknown sample, then we can identify what that substance is. Every different substance will have a specific density that does not change depending on the amount of it. Okay, an extensive property, this is a property that does depend on the amount of substance. For example, the mass. So if you have a sample of gold, okay, and you measure the mass of the gold, but you don't know if it really is gold or not, the mass of that sample will not identify what it is, okay? But if you take that sample that you think is gold and you measure its mass and you measure the volume that it displaces, then that number of density can specifically identify if it's gold or not, because the gold will always have the same density at a specific temperature at which it's measured. Okay, so now we're going to take a look at two example problems that I would like you to kind of think about and work through on your own, and then I'll go over the answers. So the first question is, the density of copper will decrease as its temperature increases. Which statement accurately describes the changes in the sample of copper when it is warmed from room temperature to 95 degrees? Okay, so we are heating it, room temperature to 95 degrees, we're increasing its temperature, so the density should decrease. Okay, which of these is correct? All right, this last example here, we have three different pictures of different substances. So A, B, C, D are different substances, and they are being compared with water. So these are liquids in a container, and you can see which substance is lighter and heavier in each scenario. And what you're going to do is rank the density of A, B, C, D, and the water from the highest density to the lowest density. So take a minute and try that on your own. Okay, so let's take a look at the answer. All right, so the density of copper is decreasing as its temperature is increasing. Density, mass over volume. We're not changing the mass of the copper, so we're not changing that mass in order to change the density. So that means the volume, something must be happening to the volume. It's pretty common that when the temperature of something increases, that substances expand. Okay, and so if they're expanding, that means the volume would be becoming larger, and if this number on the denominator is becoming larger, that would make the density number smaller. So it makes sense that the sample expands and the volume would increase to cause the density to decrease. Okay, all right, this one here, A is more dense than the water, okay, but the water is more dense than the B substance. So really the A should go here, it's more dense than the water, and the B is more dense than the C. So really we could put another here like that, and then we would have A is the most dense, and then water, and then B, and then the C.